Never inevitably be wrong. I'm a physicist, not an English teacher. Black holes? Aliens? Okay, guess not. Sure, fine. We'll move on.
Hey, can we go back to aliens? Wait a minute.
Nope, nope, have a chance.
man.
Nope, everybody have a chance. Nope. Okay, now then, let's ask a question. Let's ask a question here. You guys have been learning about different types of functions. The first one that I would like to start with in trying to make this become real to you. Because mathematics is a very abstract thing, one of the most abstract things, yes?
Can we not tell them what it's going to be and see if they can figure it out?
That's fair.
Because I have it set up to collect the data on my laptop.
Oh, that's fantastic. That's fantastic. Okay. This still stands though. You guys have talked about exponential. You have talked about linear. And have you introduced quadratics? Okay. Someone tell me the hallmark. What is the thing that makes an exponential function exponential? Like if you were to look at it, how would you know? Or what does it feel like? How is it different from linear, let's say? It doesn't have to be an equation, just what does it feel like? Yeah. A constant multiplicative rate of change. It's very well said. What does that mean? That's a great vocabulary answer, and a correct one. But what does that mean?
I couldn't tell you because I've been looking at it.
That's fair. No, that's a fair answer. That's a fair. You've also just been introduced to these things. That's fine. Anyone else have something? That's how you raise your hand. Same thing. All right. Cool. 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 That's fair. Okay. What about linear? What makes a linear function linear?
It's a constant additive relation.
Okay. Very similar and a correct definition. What does that mean? Repeated addition. Okay. So you add 2, let's say, and you take one more step and you do what? And you take one more step and do what? Okay, so you see that one? Okay, okay, cool. What about quadratics? Huh, that was a little interesting. All right, all right.
I was like, we did 1 day of quadratics.
That's fine,
so
no,
far.
that's fine,
Yeah,
I'm
yeah.
fishing, it's fine. It's
Yeah,
fine.
yeah.
You guys think about it. Well, what I'm going to attempt to do for all of you today, and with all of you, is help you guys discover where these things come from. There's a big fight, is mathematics invented or is mathematics discovered? Did humanity just come up with math and all these equations, or did these math things exist before we knew they existed, and we just found them? Let's see if we can answer that today. First thing I have is a dice. A die, correction, a die. Let's play a game. Let's say if I roll this die, and I get 1 through 3, this little dice stays lonely. But if I roll 4, 5, or 6, this dice finds a friend. And now there's 2 dice. How does that sound? And then we'll roll again. And apply the same rules. And then roll again and apply the same rules. Let's just do that a few times and see what happens. How's that sound? I will need your help. So, first dice. Got it. Good catch. Okay. Let me. I'll start. Oh, you got it ready to go
Yep,
here.
got it ready to
Let's go. So, we're at 0 rolls. We're starting out. How many dice exist?
1.
Only 1. However, we're about to make the first roll, so roll it. Tell me what you get.
Oh, 4.
4. Hey, so what does that mean happens?
I do know.
Nah, it finds a friend. So take the dice.
Let's give it to somebody else though. Davis, you want to get involved? Oh, no, sorry. The new
Oh,
dice. This fine. So we need 2 dice total.
2 dice. You can hand them one of those. Yeah.
Yep.
1 more dice.
Here, so we have,
Yeah.
there's the other thing. Yep.
All right. So now
Okay.
we are at the second roll.
1.
Okay, yeah, okay, we're good.
We are now at the second roll. So go for it.
We both do it.
Yeah. Both. Yeah. They both exist.
Yeah, 5.
So yours stays lonely, but yours finds a friend. So now, here we go. We have 3 dice. Go for it, roll again. Here we go. That's a 1. That's unfortunate. Okay, what'd you guys get?
5. Alright, so we got one more die.
One more, okay, so now 2 stay lonely, 1 finds a friend. So we have one more here. Here you go. All right, and go for it. We're gonna do this a bunch, everybody. Try to keep it on the desk. I know they like to run away. Okay, so remember,
What did
if
you
it's
get,
4 through 6, it finds a friend.
So, you did get a 4?
Oh, it's alright, you got a 3.
Oh, why you gotta lie to us like
Don't
that,
lie,
baby?
no.
Yeah.
It's 4 right here.
It's very important to
What did
have
you
it
do?
correct.
So we had 2s, we had 2 of them.
2 of them that found friends, so now we're at 6.
So let me grab
Who
some of
wants
the dice and I'll share the love on the other side.
Yep.
All right.
That's 1. Who wants another one?
There we go.
Alright?
Alright, one more die needs to be passed out.
One more?
Yeah.
Just one more dice passed out. We'll get one over there on this side.
Yeah. Alright.
Don't worry, everybody will get one.
Everybody's probably gonna get a few.
I gotta
Yeah.
practice my shot.
Okay, everybody, we're gonna need to pick
Alright, so
up
how
the
many
dice.
dice do we have out right now? Raise your hand if you have a die. 1, 2, 3, 4, 5, 6.
Perfect. All right, roll it. 4 through 6,
Okay.
find a friend.
5.
Raise your hand
Raise
if
your
you
hand if you
found,
got a 4, 5, or 6.
if it found a friend. So
So
3
3.
more. 3 extra get added, so now we are at 9.
Leah, did you have one or was that Jacob's?
That was
It
it.
was just Jacob's. Okay, so who all rolled a 4, 5, or 6?
It was, I believe 3 people did.
I think Leah raised her hand as well, so just 2. Okay, so we need 2 more die.
2 more. I got one right here. Here you go.
Alright. Kelly?
1 more dice handed out. All
I
right,
guess you did 1 next time.
and everybody roll it. Raise your hand if it found a friend. Raise your hand if it found a friend.
We got 2 friends.
2.
Just 2.
Okay, so we upped it now to 10. We're at
Alright.
the
I got one
7th
here.
generation now.
You got one already?
Yeah.
Xander, you wanna roll? Alright.
Great.
Okay, 10 total dice. Roll it.
Oh my God.
4.
Yo, you gotta actually roll these things.
What's 6?
Roll
Raise
it.
if it found a friend.
Raise your hand if you found a friend.
4 through 6 if it found a
1,
friend.
2, 3, 4 more.
5.
5, 6.
Wow,
Oh, man.
boom, okay, we
That was
caught
a
up
huge
there.
jump. Okay, okay. So we need to put out 6 more die. Who
6
wants to
more
die?
die.
Deidre?
1,
Mary wants to die.
2, 3,
I got 2 right here.
4,
2.
5.
I did 2.
1 more.
1 more.
Who wants it?
Taylor wants 1.
There we go. All right, roll it.
Roll it.
3.
Again, raise your hand if you found
4,
a
5, or
friend.
6.
1, 2.
6, 7, 8.
Have what?
8.
Sounds like 8.
Yep.
Alright. Alright, so raise your hand if you don't have a die yet.
Put your hand down. Raise your hand if you don't have a die.
2, 3, 4.
5.
Who else doesn't? Does anyone not have one? Alright, that's 5, 6, 7, and 8.
Okay, if you have multiple die, good job. You're rolling multiple die. Don't worry.
And show with your fingers now, at this point, how many dice you had, or how many 4, 5s, or 6s you rolled, right? So, obviously, if you only have one, still hold up a 1 if you get it. Alright, go.
Roll it. Roll that again.
So, raise how many fingers, how many
Fingers.
friends you found. Got 1, 2, 3, 4,
Did you get it?
5, 6, 7, 8, 9, 10.
Did you get it?
11.
Did you count here?
Raise your hand again.
Raise your hand high. We need to see.
1, 2, 3, 4, 5,
12.
12. 12.
12.
Alright.
Well,
Alright.
One of those.
You want another one? So there's 1, 2, 3.
I got 3 here.
So 6 have been handed out.
I handed out 5.
4.
You handed out 4?
Yeah.
So that's 9.
9. All right. Here we go. 10.
There, all of them have 2.
Okay.
Oh,
Here we go. 10.
Elizabeth said she wants another one.
11.
12.
12. Got it.
Alright, so we're up to 36 now.
36 dice. And roll it.
Rollies, rollies. Alright, raise your finger with how many 4, 5s, or 6s you rolled.
Wow.
Okay. Thank you for your patience, guys. We have to make sure we get accurate counting.
Sounds like 20? I counted 20.
Looks right, yeah.
Okay. So we gotta pass out 20 more dice.
Alright, we're gonna run out of die this way.
Alright,
5.
Who wants another?
There we go. 5, 10.
Okay, we got
Okay, here we go.
2, 3,
1, 2,
7.
3, 4,
Alright, we passed out 7.
Yeah.
Mr. Johnson, how many have you passed out?
10.
You have 10?
I passed out 10.
Okay. You did 7, and I did 3.
So 20.
So it's 20.
Yeah, perfect.
Alright. And rollies.
How long can you keep this up?
Not much longer. How unlikely. All one? Can you have 4?
This
Alright,
is-
raise your fingers. How many 4, 5s, or 6s you got?
That's a win. Oh dear.
Oh, wow.
Keep your hands up high and steady. We have to get an accurate count.
24?
Oh, I counted 30.
Oh,
Okay.
that might
Hold on. Keep your fingers up. Now you only got 26.
26. I have
26?
Yeah, that's
Yeah.
26. Alright. Let's see if
Verify.
we can do a whole nother round. So I think we got 26 dice
We
left.
have a lot of dice.
Yeah, we got a lot of dice.
Okay. Who wants another? Here you go. 1, 2,
Now we get into my specialty D20 dice.
4.
Alright, I passed out 4.
5. Here you go. 6. Here you go.
I'll wait for that to get done.
Here's what we use for Dungeons and Dragons.
Plenty here. 9.
Straight up.
10.
Alright, I passed out 8.
How many?
So 10.
We need
8 more.
8 more. Got it.
Alright, I passed hold on, hold on, back up. How many have you done?
Now 11.
Now 11. I've done 11, so 22.
Okay, so we need 4.
4 more.
4 more. I got it. Okay.
We can do math, guys, I promise.
1. Here you go.
2.
Here. We're good.
Huh? Are good? Okay, great. Okay. I got a couple.
Alright.
This is probably going to be the last round.
This is probably going to be the last round. Alright, rollies. Up, go. Whatever's facing up. It's still whatever's facing up. Yeah, but it's still.
Oh, I've still got like 30 dice in this.
So, sorry. Guys, if you have something other than a D6, I should have thought about this, just use the top half. So, like, these are D10s. They have essentially 0 through 9.
Mhm.
If you have a D20 like this one, 11 through 20, etc. So, just use the top half, essentially, is what it is.
All right. Hands up high once you have.
Could have also just done even versus odd.
That's fine.
We're here.
It worked well until we had the extra
The
dice.
extra dice, it's fine. Alright.
5? Jeez, okay.
I know.
I got like 49.
I got 48.
Okay.
40. Okay, that's.
I just got 46.
We'll
Close
split the
enough.
difference. We'll say 48.
You know what?
You know.
It's within the margin of error.
Yeah.
Got about 30 or so dice in this box.
Yeah, it's fine.
So the reason we're
Wait,
stopping
we
now.
still have a lot. Oh man.
The reason we're getting close to stopping.
Yeah.
Look how many dice we're supposed to be rolling this round. We're supposed to be rolling 130 dice this round. Let's pause. I want to call it here. So what do we have? On this column here, our independent variable is going to be which roll we're on, which generation we're on, if you will. And then on the dependent variable, we have how many dice happen to be a part of that roll. Can you see there's a connection here? Just with your eyeball. What happens as we increase in our generations, as we go farther and farther down? What is happening to the number of dice we have? It's adding more of them. There's more and more and more and more of them. So what's the best way to see a relationship between these two variables? It's probably not by staring at the numbers.
To be fair, if it was true math, it would be. But it's not true math.
I'm a scientist, not a mathematician, so I don't see the numbers as clearly as some people do. What we like to do as scientists is graph everything. So, I submit to you, we should graph this with our dependent variable and independent variable.
Quick question, does anyone have a theory of what type of function we're about to look at?
Oh, that's a good point.
Exponential?
What leads you to believe that?
Because you were talking about adding dice earlier, so why exponential?
Okay. He said he doesn't expect it to be a straight line.
I was saying, if we look at that graph, do you expect it to be a straight line? No. Even though we were adding dice, remember we were adding pennies, right, with the dream job salary task? But eventually, those pennies kept adding up in a way that we were doubling, right? Remember that detail? All right. So rolls and dice.
Hold on, it's not, in fact, linear. If you had to guess, now that we can visually represent them as opposed to numerically representing them, what does it look like? This is screaming an exponential of some kind. But which one? Right, exponential is a class of functions, but as some of you may know, there are different, what are those called, parameters, different numbers in that. A coefficient in front, or
I would say, which
a number.
equation should we be thinking about if we're talking about an exponential?
There we go.
B squared or b to the
X, there we are. Well
because
done.
it's changing how many times, right? We multiply by that b.
Yep. So when I say parameters, I'm speaking like a scientist here. This A can be any number that we want it to be. This B can be any number that we want it to be, but the X must be in the power of B. This is what makes it an exponential function. So what we can try to do now is figure out what does A and B need to be, or what do they need to be, in order for this function to fit or describe the reality of the dice growing. Now normally, there are processes that we can walk through this. Linear regression, things like that, that you may or may not be talking about at some point in the class.
So actually, yeah, so what we're going to
perfect.
learn about eventually by the end of this year is how to take that curve, make it a straight line, fit a line to it, and figure out a regression. That so that we can make a prediction. How many dice do we expect to see on roll 13, on roll 14, on roll 20? Right? Because I can't get to roll 20. I would have probably 1,000 dice at that point. So I can't do that, but I can make a prediction, right? That's what we're going to eventually end up getting into.
So
but we're not going to get to that right now.
The point is there's a process that you can do this.
Can I go ahead and, so I will say with the calculator.
But the computer here
Yeah.
has an ability to do it very quickly for you, almost in an instant.
Let's see if I can make this a little bit bigger. No, that's not what I want.
There we go. Can y'all see that okay?
See, they can't see this though, which is what I want to see. If I go down here, it says show exponential.
Check that out.
That's ugly.
See the line? That fits pretty well. I mean, it's not exactly on it. You notice that some of the points are a little below. This point's a little above. Why isn't it exactly on the line? Why isn't the analytical, the perfect mathematical function seen here?
Say again, Peyton? Kind of.
Kind of. We'll figure that out in a second, but I'm trying to take something, again, I'm a scientist here, trying to show you how the math comes alive. Why aren't the data points exactly perfectly on the line? Shouldn't it be? You are seeing or discovering something about our world. Real data are messy. There are unpredictable variations in factors. How about this? Wasn't there a chance that in our 100 some odd rolls that everyone rolled a 1? I mean, that possibility existed, right? And what would have happened if everyone had rolled a 1? The next generation would have had 0 additions. We would not have walked up this graph any at all. So the chance existed for something improbable to happen that would skew it off of this perfectly growing function. And those small, subtle little random variations cause, in the real world, small, subtle, sometimes not so subtle, variations, deviations away from the perfect function. But even with those, this analytical function, this fit that we have found, this exponential for this population, is what best describes it. If we took away the randomness, this would do it perfectly.
really quickly, I want to connect that to something we studied earlier. Remember when we did This American, we found the average word length, right? Did everyone get the same average word length when they did their sample? No. There's this thing called sampling variability, right? Like everything, especially even random stuff, we may get a nice normal curve out of it, but random stuff is going to have variability. Dice are random chance. They're going to have what? Variability, right? When I teach AP statistics in the spring, like a big part of what we're going to study is, hey, how can we account for that random variability within the parameters of mathematical ideas so that I can make predictions about the real world? It's a really, really cool concept. But yeah, math is beautiful because it explains the world, but is the real world perfect? No, right? We're going to have messiness. We're going to have variability in there. That's where that's coming from. Now, can I talk about that equation really quickly?
Now, yeah, perfect. That's what I was about to lead to.
Really quickly, I do want to point this out. That's an ugly number, right? It'd be nice. I'm pretty sure you do some rounding on things, right? I'm trying to be precise as can be.
You have to round at
but
some point.
What's a number I could probably round this to? 1.5? Would that make sense,
Yeah,
Dr. Johnson?
absolutely. That's a perfectly reasonable rounding to do.
Okay, so what does this mean is happening mathematically with the dice? Like, let's put this in the context of the dice. What is that 1.2? It's the y-intercept, or what else do we know about that 1.2? It's the starting value. Something else I know with it. Come on. What do you know about every y-intercept that's ever existed? The input is what? Okay, and what was our input again? It was the... So at 0 rolls, we had 1.2 dice? That doesn't make sense, does it? But is the real world pretty, or is it messy? It's messy, it's just an estimate. Remember how we had averages, right? We're talking about the average letters per word. Can you have 4.2 letters in a word? No, that's the average. That's what that is, right? It's an estimate that on average we had 1.2 rolls. So what's happening here?
If you were to round that 1.2, what would you probably round it to? 1. And how many dice did we have at the beginning? Do you see how it's close? Okay, I put that in mind.
So what's this telling us is happening to the number of dice? It's and not just multiplied. What's it doing? It's being repeatedly multiplied, right? Because what's the rate of change again? You said earlier? Constant multiplicative, because remember, constant means it's the same. Multiplicative, it's the same multiplication. That's what we mean, right? The same multiplication all the way through. Now, Dr. Johnson, why is it 1.5?
That's a great question. What if it was just 1? 1 to the x power. Remember, x is what roll we're on. That's the independent variable here. So if it was just 1 to the x, what do we do on roll 1? 1 to the 1 power. Did we grow? What if it was 1 to the 2nd power on the second roll? What about to the 3rd power? To the 4th power? Are we growing? Are we?
Well, pause and think about it, guys. What's 1 times 1 times 1 times 1?
It's not growing. Interesting.
We didn't grow, right?
So if it's a number larger than 1, however, let's say it was 2. What's 2 to the 1st power? So that's the first roll. What if it was 2 to the 2nd power? Yo, we grew. 2 to the 3rd power. You see what's happening? So apparently it's not 2, it's 1.5. I'm gonna throw this out here and let me know if you believe this or not. You know what probability is? Yeah, pretty much. It's the chances, the fraction that something will happen. Probability is defined as the number of successes divided by the total number of attempts, the total number of chances that you have. So if you have 100 marbles in a bag and 2 of them are red, the probability of you drawing a red marble is 2 out of 100. Make sense? What is the probability of the dice growing. Your dice, what was the probability that it would find a friend? What numbers did you roll? What numbers did you need to roll in order for it to replicate? 4 through 6. Of the total number of dice, so there were 3 numbers, right? 4, 5, and 6. So probability of growth, there were 3 numbers that were possible to be rolled, but how many numbers were on the dice? Therefore, what was the probability of growth? You can simplify that, right? 1/2. Or a 50% chance of it growing. Everybody with me? Believe that? Did any dice die? Were there any numbers that would cause the dice to be removed from the population? No. So, what was the probability of survival? 100%. 1. There was no way any of them could die. With me so far? So we have a probability of survival, a probability of growth. There was no probability of death of the dice, if you will. But instead of the percentages, let's write them as fractions, because that's what probability is. It's a fraction. What is 50% as a fraction? 0.5. What about 100%? 1. Wait a minute. What do you see? What do you do to these 2 numbers to get that one? Look at that. The number that is the base of your exponent is the number that is telling you something about the survival, growth, and death rate of whatever the thing is that's replicating, all wrapped up into one number. There was a 100% chance of survival with an additional 50% chance to grow every single roll. Here's a question. What if there was a death rate? Let's say what do you want to say? Let's pick one. Let's say there was a 1/3 chance it would die. You rolled a 1 or a 2. What is that in fraction form? Sorry, decimal. But what is a death rate? That should be negative, right? Like effectively it's a negative, right? You're taking away. How would that affect this number, do you think? It would take away from it. So this new base of the exponent would be probability of survival plus probability of growth minus probability of death. And all those together would end up equaling the base of that exponent. Where do you think this would be useful in the real world? Notice I've been changing my vocabulary. I didn't talk about growing or finding a friend. I said growth rate, survival rate, death. What am I talking about? Populations. Where does the exponential function exist in the real world? It exists in one place with life. This is the mathematics that you can start with. These are the mathematics you could start with to begin predicting and modeling the deer population every spring, or the alligators in Florida, or people on the planet Earth, or bacteria infecting someone, or the growth of cancer cells. It's all this. The only difference is
Spread of growth.
or the spread of a virus in a population. Absolutely. It's this. And now you know why. Hopefully, we've established why understanding this function is not just a test question. This is discovery of how something like life works. There are other places it can be applied to as well, such as radioactivity. Radioactive decay is one of the most important ones that we learned about as physicists. How quickly do uranium atoms fall apart and release their radioactive badness? Or goodness if you have it in a power generator. You take this exponential growth function and you flip it around and you do that.
Okay, I think hopefully y'all talked about carbon dating with biology and dinosaur bones, stuff like that. No? Does that sound familiar?
A couple of nods.
Not a lot?
Not a lot.
Not quite. Okay. Okay. If you ever talk about carbon dating, it's based on this exponential decay. The amount of carbon in your
14.
bones or in a person's body decays at an exponential rate.
Yep. So when the moment you die, the amount of carbon-14 specifically is locked in. And since you aren't living anymore, you're not able to take in more of this carbon-14. And it slowly begins, actually quickly at first, but then slowly begins to just fall apart and disappear. So if you dig a bone up, it has to do with life, but you dig a bone up or a tree trunk or something, and you sample how much carbon-14 there is based upon everybody we have today, you'll notice the dead thing has less than we do today. You can measure how much less it has to get an age, roughly. It's not perfect, like it's a few thousand years-ish errors, but if we're talking about something that's 60,000 years old, you're fine. We're just getting an idea. We're not trying to nail down his birthday or anything. This is exponential. Just instead of growing, it's decaying. But it's the same function. Do you just put a little negative here or not? The negative makes it die and decay down. Positive makes it grow. I think this is cool. Samesies.
Apparently I'm struggling on it. It's okay. It's a Friday. I get it, guys. Kyron's like, I'm not sure, Mr. King.
Quick questions. Anybody? You have a question? Thought? Snarky remark?
He's got a date, right?
Yeah.
He left. I feel like we need to get up out of desk.
I think so.
You think it's time for that?
I think so.
You think they're ready for the cards?
I believe so. Let's try it. Okay.
Let's start spreading those out.
For the next thing.
Oh, if you could help us, yellow foam dice.
I'll stand over here. What these are, as I said, devices from University of West Alabama Physics Lab that I will be using next week for my classes in their physics lab. So these guys get a sneak peek at it. It is a tablet there. It's called the LabQuest tablet, and you can connect all sorts of devices to it, and it will measure those devices, whatever it is you plug in, temperature, pressure, motion sensor. It can measure times with little photo gates. When you break a laser beam, it tells you what the timestamp was very, very accurately. Many, many other things. We're going to be using the motion tracking functionality. So you'll notice the little green thing. That is a sonic sensor. From the mesh, it will send out little clicks, almost like a bat or a dolphin, because we're just copying echolocation that those creatures figured out a long time ago. The sound will fly out, and it will wait for a reply. It will wait for an echo, something in front of it, for the sound to bounce off and come back. Since we know the speed of sound in the air around us here, the computer can take the time delay between the click and the reply, and it will know how far away that object is to really, really precise degree. We're going to need that because we're going to be tracking the motion of a little cart. So everybody, you're going to have to get on the ground. So just go ahead, let's get on the floor, get around your tracks on either side is fine. You will notice there is a stopper on the track. Please rest the motion sensor on the track on the far end and have the little hinge tilted up so that the sensor can see a cart that we're going to be handing out. So this guy will go over here and we can tilt this up and it can watch like that. Okay, there we go. Just like that, and so you'll be able to hang off of the cart as we go.
For your group.
Right, there we go.
If you could crack that bad boy open for me.
On the other end. Yeah, because the cart is going to stop right over there.
Here's a card. Do they have a card right here?
Not yet, I'll take that. Okay, everybody should be getting also a little motion cart here. They're heavy, they're also really satisfying to roll around because they're really smooth on their wheels. Keep that right there. Okay, I have one request. Please do not break my little green sensor, okay? So when we're moving and rolling the cart around, it's okay if the cart bumps into the stopper. That's why it's there, the black stopper on the attached to the end. Do not let the cart whack into the green sensor, because those are a little expensive. Also, please be careful with the tablet. Each of those tablets is on the order of $1,000.
So we don't want to have to replace that.
I want to have nice things, so don't break it. Okay, if everyone's ready and everyone's little sensor is set up to shoot down the track, take the tablet and click the button that's at the top, a little blue-green button that's at the top left. That should wake up the tablet. On the top. Just tap it once, it should wake up.
Oh, what is that?
All right.
It should be picking
You
up
should
some
hear-
kind of distance.
You should hear clicking.
Yep.
Listen carefully. If you hear clicking, that means it has been activated, and it's waiting for you to hit play in a moment. Let's go and adjust this so right now it's hitting the track. It's not getting angle it up so it's there. No, so it's going down. All right. Everyone at the top of the screen on the tablet, the very top, there's a tab that looks like a graph. Click on that graph. It's a tab at the top right. It looks like a graph.
Top right. See it? Can I see the graph?
All right. Everyone at the graph, raise your hand. Raise your hand if you were at the graph. Good. Now, in case, just to make sure everybody's on the same page, on the tab options where it says File, whatever, go to Graph. It'll be a drop-down menu that says Graph, Show Graph, Graph 1. Just to make sure everybody has that same. So I saw a couple that weren't there, so he might have reset while he was asleep. Graph, Show Graph, Graph 1. Oh, yeah, that's good. Yeah.
Hey guys, there's 2 Carnegie Learning textbooks near you. Grab those, put the sensor underneath that.
That's
That
a good
way
idea.
you have the full track and the sensor is a little bit more on level with the cart on that track.
Thank you, Mr. Kenny. That's a good idea.
Sorry, I just realized.
That's a good idea. So when you do Show Graph 1, it should just blow up the graph to cover the entire screen. Okay, everybody good? Everything lined up?
Just like right before, like if you see.
Thumbs up if you're ready.
Okay, thumbs up.
Thumbs up if you're ready. Awesome. Last thing, on the tab now, where you clicked on the graph to bring up the graph, go over one more and you'll see one that looks like a table. Click on that table. I'm just showing you where it's at. Once you hit play, it will begin clicking very quickly and filling up that table. So if we need to get numbers later, that's where you can find them. Okay, go back to graph now. It looks like a little table. Yeah, right there. So if you need numbers later, that is where the numbers will be. For now, let's go back to the graph. Here is what your task is. Someone who has the steadiest hands will need to move the cart in a very slow, steady, controlled way. Either towards or away from the sensor, your choice. When you're ready, whoever has the tablet, in the lower left-hand corner of the tablet, you should see a green play button. Hit play, and as soon as you hear the clicking going crazy, you can move. And whenever you're done, you can stop it, or it will stop automatically after 5 seconds. See if you can just move the cart as slowly and as steadily as you can. And let's just see what happens with this motion that we're tracking. Go for it. If you need to reset, you can just hit play again and it will restart.
The graph is.
You got it? Okay, okay. This shouldn't be too hard. We're just testing.
What did I create?
Oh, you need to hit play. I think I said that.
Almost a line.
Okay,
Go
go.
do it one more time. Yeah. Go.
Let's see if you can move it a little bit faster and still keep that.
Yeah, but y'all need to communicate that you hit play. 'Cause he
You
didn't.
can. It'll create something different from a line.
What do you guys think? You can hit play to
What it
reset.
create?
What can I do?
Maybe so like when you have the speed the same. We created a linear function.
Play, like I said, when you're ready, hit play.
Like as he was moving the cart.
Oh,
And
yeah.
communicate to make sure whoever's pushed the cart knows that it's not to go.
I didn't even stop, like, you gotta wait.
Oh, okay.
That's
That's not
Well,
bad.
yeah, so when
There's
he
a
was
couple
moving
of
it
technical
just
difficulties.
straight, closer and closer and closer, what did it kind of look like in that part?
I did say
Like on the
slow.
grass?
That's fine.
Like
Yeah,
straight on.
that's good. It
It
stops.
stops
You're
as well,
good.
the graph?
When the clicking stops, it
On the
stops.
graph as well.
So it's not clicking anymore.
Your diligence is admirable. All right, so that looks good to me.
Hand again?
You guys, that looks good. That looks good.
So what does that look like?
All right, so everyone,
Just going down, anyone that
everyone,
Just kind of see just like, it's going like.
are you ready? We good?
Yes.
If you had to use one word to describe the graph that you see based on the motion that was performed, a slow and steady motion, what would you call that graph? What? One more time? Linear. Yeah, doesn't it look like a line? So what have we discovered? Is a linear function, y equals mx plus b, or whatever form that you guys are studying about at the moment, is that something that we just made up as mathematicians?
No.
Apparently, just like an exponential function is found naturally in life, a linear function, one of the places we can naturally discover it, is in the motion of an object that is moving at a steady, constant rate. Did you speed up or slow down the little cart as you were moving it? No, you didn't. Hopefully, if you follow directions. I said slow and steady. So, let's extend this. What else would this look like? What about cruise control on the interstate? What is constant, though? Your speed is constant. So what is a linear position time graph telling you? It's telling you you're moving at a constant, steady velocity. Huh. Now, here's a difference I want to point out for a moment. Some of you, Mr. Kenny, could you wiggle your way to the board?
Yeah.
Could you draw just a quick line with a positive and negative slope?
One
Just so
with
we can
positive
compare.
slope,
Yep.
one with negative.
Yep, just so we can compare, because some of the groups had different ones. Some of you had graphs that more resembled the right, some of you had them more resemble to the left. Raise your hand if yours looks like the left one. Okay, 1, 2, 3, so 4 groups. Did yours as well? So, okay, everybody, this works. Everyone's graph looked like the one on the left. How do you think we would make the graph on the right? Say again? Go the other way? Test it. Do it, test it right now, see if that works. That's a valid hypothesis, let's test it. All you have to do is get it set, hit play, and it will go.
Do you need help? Is that what's going on? You might need to hit play.
Okay.
It's not clicking?
Yeah, but they're not.
Yeah, it is. There we go.
That was tough, guys.
If you have both
Oh my
hands,
goodness.
it might not register.
Like right there.
Yeah, I can start it there and then start
Huh.
We ate it up.
Ready?
I feel pretty proud of that. I'm not gonna front. That's a pretty
Okay, yeah, it's a little confused because you started a little too close. Start by right here. There we go. It was the sensor, not you. Just hit play. Hitting play again will reset it.
Is that a, are you trying to say it's a good excuse?
I need.
Keep, oh, yeah, don't let go, because if you let go,
I know, right? Like, at least come
see that little hitch right there?
So it's the one left or the one
I
right?
appreciate that.
But still, you can get the idea. We don't have to do it again. You get the idea.
Alright, yeah.
High school.
All right?
Seems
So,
like
thumbs up if you're ready.
this might have worked.
When you change direction, what happened to your line? Which one did it look like? Huh. So not only is a constant and steady rate of change of position, aka speed or velocity, indicative of a line, the slope of the line, the direction the line is going, apparently is also connected to your motion. If you are moving away from the detector, it looks like it's a positive slope. You're increasing your distance from it. What happened when you decreased your distance from it, when you moved towards it? What kind of slope did you get? A negative slope.
Notice increasing distance because we're constantly what?
Constantly adding distance.
Did you notice how the cart, well, how was the cart moving in respect to the sensor? It was getting further away from the sensor, right? So what was happening to the distance? It was increasing.
Increasing.
But I think everyone started by moving the cart towards the sensor, which was causing the distance to decrease. So, once again, it's a linear function. So what should we immediately think about it? As soon as I know it's linear, or to lead me to get to linear, I should immediately be thinking about what major I get. Constant, additive rate of change called what, Shadidra? Slope, right?
The name of that is slope. Very good.
The name of that constant additive rate of change is just slope.
Again, my job here is to try to help you see these things in the real world. We as physicists, you would be shocked how many PhDs come from somebody graphing a thing and saying, I think there's a linear relationship here. Let me find the slope of this thing. And then all of a sudden, 4 years later, you have a PhD. I'm not even joking. It's because people haven't ever thought to link those two things together to see if there was some kind of relationship, correlation, additive rate of change, or even multiplicative rate of change. So these things are still being found in the real world, and we are able to utilize the construction, the framework of mathematics, of the linear function, of the exponential function, to discover how and why the world does what it does. Math is useful because math is the language of the universe, insofar as we have found. That's a very poetic way to say it, but it's pretty true. All right.
Can we take
Yes.
2 minutes to let them stand up, move around?
Yes, of course.
Sit on the ground for a minute?
Of course.
Some of us need to move a little bit, is that fair?
We're almost, we're getting close to
I think we're about to do gravity next, right? Is that you're
there's
about to-
one quick thing I want to show them.
Oh,
With
sorry.
this, with my syllabus. All right. What do we know about slope? It can be positive or negative. What else about it do we know? It can be greater or lesser. What does that cart have to do in order to have a slope of 0? Test it.
Test it. Somebody else said not move.
Somebody said not move. Test it. Does it look flat, or did it look flat before the thing zoomed in? Did it look flat before it zoomed in? It auto zooms and makes it look kind of gross.
Oh my god.
It auto zooms and makes it look gross, okay, but while it was being tracked, did it look flat?
It looks flat.
It did look flat. So a slope of 0, that's still a line, that's still linear. But what does that mean? If we see a slope of 0 in a motion diagram, what does that mean the object's doing? Nothing. How do we make the slope greater? We know to have a non-zero slope we have to move, but how do we make the slope greater? So what you said? Well, the track hopefully is kind of level. It's not supposed to be going on its own right now. Faster? Okay, test it. Just don't hit my sensor. Go either direction, doesn't matter what direction. All we're looking for is the steepness of this slope. Does moving faster make it
Move it
steeper?
with your hand, just faster than the way Lando's moving.
Sorry, I missed the button.
We're not pushing it down to the end. So just faster than Lando's moving.
That for me, like.
Don't be afraid of it, like you scoot it. You can also stop it prematurely. Those who with the tablet, you can hit stop before the 5 seconds is fine.
Yeah, I know.
So did it look pretty linear but steeper
What'd you
early
find?
on? Steeper than when Landon did earlier?
What'd y'all find? Oh, you can't see it. What does that look? Well, that's a
Go
little
ahead
curvy,
and
so it looks like
again.
moving.
Go ahead and just grab it and
Hit
just
play.
move it.
We'll do it
Keep
steady.
it consistent, but still
Hit
get
stop.
stop complete. So I mean, like move it faster.
And just took
That
advantage
would
of
be
it.
faster.
I was late to go get Chick-fil-A.
Closer.
I was like, I'm gonna already anyways, I might as well.
What do you
You don't
think?
want to push it. You don't want to push
Who
it.
cares about Mr. Kenny's out 3
Does a faster motion, faster velocity equate to a slower?
Where's mine?
Yeah, not just like that.
Yeah, you don't want to let it go.
I'm a human being.
Does a faster velocity equate to a steeper slope as opposed to the
Yeah,
next
exactly.
That was me moving
Okay,
fast.
I'll go next time, I'm right.
Hit it one more time, so you can see the comparison and move.
But I had it.
Yeah, you had
I
it.
didn't think about you.
Oh, thank you.
But you did have it. It was very. You guys notice how
Was fast steeper.
Like good.
Watch it bring it up.
it like went down.
So, this, yeah, there you go, that's what I wanted you guys to
That's what we're
see.
getting at here.
Did y'all see it?
She said that she.
Oh, yeah, that's good. All right, so with the this is the conclusion of the linear section now. Everyone can stand up. We saw that the slope, the parameter of slope is
You can
in
stay there
fact
if you want.
the velocity of the object. The faster it moves, the steeper the slope. The direction it moves is the sign of the slope. Positive with increasing additive rate of change of distance, decreasing with a negative or a negative additive rate of change of, that's a weird way to say it, subtracting every time that you go. All right. Any questions on that quickly? Do you see the connection between linear functions and real life now?
Yes.
That's the key. That's what I want you guys to start. The motivation behind why this matters. All right. For the last thing, we're going to look at something a little different. With the cart, you were steadily pushing it, right? A very constant, steady rate. Was the car speeding up or slowing down while you were pushing it? No, it was steady. That's what we just said. But what if something was speeding up or slowing down? What if there was something pulling it, like gravity? Something steadily pulling, constantly affecting the motion. What would that do? Any guesses? How would that affect the graph? Any guesses at all? It's okay to be wrong. We're throwing spaghetti at the wall and seeing what sticks.
Have you ever heard that expression before?
I love that expression. You just throw spaghetti at the wall, see what sticks. It would be what? That is a very specific prediction. It being a parabola. What led you to that? Why would you expect it to be quadratic? Context clues! Well done. Very, very well done. I would be remiss if we did not cover quadratics as well. So the hypothesis here is this is going to be quadratic, not because physical reality might make it that, but that Dr. Johnson has a story to tell. Okay. So how much time do we have again?
20 minutes.
20 minutes. Okay, good. So I see the books everywhere. Do we want to just go straight to the basketball, or do we want to?
I would
do
say
cards?
let's do the carts first,
Okay.
and then let's say 5 to 7 minutes to collect data on the carts.
Cool.
Then basketball,
Okay.
because I want that to make sense
I see.
before, because the basketball doesn't make a whole lot of sense until.
You got to zoom in
Yeah.
on the spot.
Yeah.
All right. So we're gonna go back to the carts. Everybody's legs still okay? Stretch, walk around a little bit. Yep. So we're about to go back down again. You guys are young. We can do this. I'm not that old, but I can say that. All right. What we're gonna do is allow this constant, steady pulling, this force, to act on the cart. But in order to do that, we need to let gravity act on it. So what we're going to be doing is inclining the track a little bit. For that, you can use books. You can...
Can I model it really quickly?
Absolutely.
What I would probably do is I would grab some books like this, okay? Put the, this has to be 4, right? So there, it's nice and elevated. I would put my sensor here, and you can let the cart go down. Make sure you grab it before it hits the bottom. Or you can slide it up, just make sure it doesn't go off the end and hit the sensor, right? So up and back down.
You see how Mr. Kinney did that? He didn't hold the cart pushing it up. He just gave it a little tap at the beginning and let it roll up on its own and roll back down on its own.
And it's real easy to give it too much force, so make sure you're protecting that sensor.
I would recommend doing that one first. When it was not being actively pushed and sped up or slowed down. What described the cart's motion? Linear did. That's steady, constant cruise control, not speeding up, not slowing down. But the moment something was actively pushing to speed up or slow down, what new function describes the motion? You're looking at it. Quadratic. That's pretty cool. So, not only do the parameters of the function give us information, the literal identity of the function gives us information. If I were, as a physicist, looking at an asteroid, for example, flying through space and tracking its motion, and I see a linear function, I know that there's nothing actively pulling or altering the trajectory of the asteroid. But what if I plot it and I see a curve forming? Immediately, what do I know is happening to that asteroid? Something is pulling it. Something is deflecting it. Something is drawing it nearer. Actively pushing or pulling. Acceleration is what that's called. That's probably pretty useful if we want to know what an asteroid is about to do. Ask the dinosaurs. Oh, you can't, that's right, because they're not here anymore. So, we have with the linear functions, the slope tells us the velocity. What are the parameters of a quadratic function? Well, what is a quadratic function, first off? What defines a quadratic function? Have you guys talked about that yet?
We just hit on it yesterday for the first time and
Okay.
barely touched on it.
This is a new thing, that's fine. Does anyone remember? Anyone have any context for this? No is acceptable, and you can just say it.
No.
Thank you, there we are. No is always an acceptable answer, okay? As long as you're not being mean about it. All right. What do you notice about the shape? Is anything constant at first glance? Is anything steady at first glance? No, it's not. Except maybe the concavity. The shape. Is it holding water or is it dumping it out? Concave up, concave down. That doesn't change. Wait, concave up, concave down. That sounds like something. Slope up, slope down. So you can see the parallel. So if it's concave up, let's form a hypothesis. If slope, positive slope, meant that it was increasing the distance away from you, I wonder what concave up would tell us about the acceleration, would tell us about the force that is actively pulling it. What do you think? If it's concave positive, concave up, what might that tell us about the force behind the scenes? It's a positive force. Yeah, a positive force constantly pulling it away from the detector in the positive direction. What if we had concave down? It's constantly pulling it towards the detector, decreasing distance. Everybody take a look at your setup. What direction was gravity pulling the cart? Towards or away from the sensor, trying to increase or decrease the distance from the sensor. Look at your track. What direction is gravity pulling? Away! It's pulling it away from the detector, increasing the distance. Does that sound like a positive or a negative to you? Increasing the distance, does that look like a positive or a negative to you?
Positive.
And what was the concavity of your graph? Up or down? Positive or negative? There it is.
Yes, hold on to that, because that's Monday.
Let's go. Spoilers! Okay. All right. That's all I want to say from the background. We have numbers up here now.
Yeah, number. So, so remind me of this again. A linear function has what type of rate of change? Not just additive. Constant additive, right? Meaning we are repeatedly adding by the same amount over and over and over and over again. And exponential was constant multiplicative, right? Remember, we got to keep those words constant additive and constant multiplicative there because they matter. But then we looked at the dream job salary task yesterday. Not dream job. Whoops, sorry. Gold rush task yesterday. And when we looked at that gold rush, we had our base, we had our area. I think it was like 0, 0. When this went, it was 5 by 45, right? So it was 225. 10 by 40, so 400. 15 by 35, so 525. Yeah. 20 by 30 is 600. We got to that 25 by 25, which is 625. Does this area kind of look familiar? These values, okay? And so remember we looked at it and we said, hey, man, that's not the same thing over and over again, is it? And it sure wasn't. But what was happening? What did we say was happening there? It was what? What was decreasing by 50? What is this right here? Someone said it? The rate of change, right? This is my rate of change. Ooh, that's close. This right here is my rate of change. And what's happening to that rate of change? It is decreasing by 50.
Ooh, that's constant.
That's constant, right? Wait, what was constant additive again? That was a linear, right? So this is constant additive. So this rate of change was a linear additive rate of change, right? Do you remember that now? Hopefully that rings a bell. So now when I look over here, okay, so we've got our position. I grabbed some data from Mary, did I steal y'all's? David, I stole y'all's? Okay, I'll give yours back in a second. But I stole their data, and so that's where this is coming from. We've got our position here of their cart, right? Notice the position is decreasing. The cart was getting closer and closer to the sensor, right?
This is on the way up, it sounds like.
Yeah.
Yeah, time. This is while it's on the way up the track.
Correct. So, yeah, the position was decreasing because it was going up the track. Thank you. So notice I took the differences. That's why I said diff 1, right? So what I did was to find out how it went from 0.851 to 0.811, I just subtracted them, right?
You found the change between those.
0.851 minus 0.04 is 0.811. 0.811 minus 0.039 is 0.772. I point that out because I can't draw it in between like I did over here. Notice that's not constant, is it?
439, 37, 34.
And it's not really constant here. That's the one that's crappy underneath that. I'm like, it's not constant here, but man, what is that really close to almost every time? What's that kind of
It's
average
hovering
around?
around.
Like if I were to average all those numbers, what do you think it would be? No, come back, that's not. Sorry, Alt, Tab.
SOHCAHTOA, go away.
Yeah, there we are. Yeah, that was matching stuff. Alright. Guys, what numbers do you consistently see show up? What is this center
Point, yeah, go
around?
with 2.
0.002? Right? So, why is it not 0.002 every time? Like I thought in quadratics it's supposed to be that linear additive. Why is it not 0.002? Dr. Johnson talked about this earlier. What were you saying, sir? So math's not messy. Math is perfect. Math is beautiful, but what's messy? The real world, right? So if this was perfect, what do you think that was supposed to be? So 0.002, right? So if in an ideal world, a 0.002 here, so this would be constant additive. So this rate of change right here had to be what? Linear additive. Wow, I don't know how I got that far off. It's had to be a linear additive rate of change, and because it's a linear additive rate of change, we know the position function is what? What type of function did this have to be to have a linear additive rate of change?
If you need a hint, look down at your.
Look at your graph. What was
What
it?
shape is that?
Quadratic, guys. If you have, and so remember, I want to always emphasize this. Do you have to just look at a table? No. Do you have to just look at a graph? No. Do you just have to look at an equation? No. They all look different, but they're telling the same story,
There you
right?
go.
That's the beauty of mathematics, is that they're telling the same story. We have 5 minutes.
All right,
Sorry, I just realized this.
no worries. So, I think of quadratics as almost like it's nested. You're looking at the rate of change of the rate of change.
Right.
And then that second layer to it. Because quadratic functions are a little more complex. So that's to be thinking about that when you see kind of a nested hint. Look at the rate of change of the rate of change. It may help with that. What was causing this? What was the pull? What was the source of the thing accelerating the cart? Gravity. But was it all of gravity? No, because you're on a track. It wasn't just falling, it was sliding. I wonder if what would happen if we used our sensor to actually look at something that was really falling. Like the basketball. So, we're just gonna do this one ourselves. Honestly, if you guys probably at this point, you can, if you would, grab your sensors, take them off the floor, please, with the tablets. And we need to put those somewhere safely. So at the moment you can hold them and put them at your desk, but you guys can stand up and go to your desks right now.
You use X for position, don't you?
I do absolutely use X for position.
Take one.
3, 2, 1, go.
Okay, good.
Beautiful.
Sweet!
All right, we got a few bounces.
Yeah.
All right, so everybody, so we've watched it bouncing a few times. You guys look up here, see what we see? See, you can see the bounces that are there, right? You can see the bounces. Can you guys see back there?
What does each bounce kind of look like? Or after each bounce? what does
Every
it look
little
like?
bounce, what is that?
Concave up what? Concave up. Starts with a P. Parabola, meaning it's what type of function? Quadratic, okay?
All right, so then, turn it around. There we are. So what we can do now is actually fit this with the fit position. Not that.
Quadratic, yeah.
There we go. So I can, on the tablet, do the exact same thing that Mr. Kinney was doing
What
up
was that
here
equation you got?
and fit this equation of the parabola. I have,
Right there.
got it, I have x equals 4.8157 at x squared plus, or sorry, minus 8.7413.
Minus what? Say it one time.
8.7413 plus 4.4585. Yes, that's an x, sorry. 4.4585.
Alright.
This is pure gravity right here. And what I want to point out is this number right here in front of the square, because the square term is what makes it quadratic.
Remember how we looked at that yesterday? We looked at the difference between that quadratic and the exponential was, an exponential is like 2 to the x, but the quadratic was x squared or b squared yesterday.
So, this is the piece that actually makes it quadratic. This is a little linear piece here. 4.81. It's an oddly specific number if you guys have had physical science or physics and know all before. What is 4.81 times 2? I'm saying that kind of arbitrarily, but what is that about?
9.62. There we go.
Is this number, by chance, familiar at all to some of you? Almost, something close to this number for gravity. What's the actual number? I'm fishing. Anybody see this?
I heard someone say 9.7. There
Yes!
you go.
9.81 meters per second squared is the pure mathematical strength of gravity's pull down at the Earth's surface. By us dropping that ball and modeling one of those little bounces and getting the curve fit, this.
Have a fantastic weekend. Hopefully you understand linear, exponential, quadratic a little bit better.
Come to the University of West Alabama. I would love to see you guys.
They do that, you saw that physics class that they can take?
Dual enrollment, we open it, it's not just open, we have to know we're in the college. We need to make sure yeah, it's restricted to only high school.
I'll make sure I talk about that.
They won't be mixed with any college students. Thank y'all so much. I did. Wait, were you in that class? Yeah. Were you in that class? All right. Okay.
So she got to see if you do the same thing?
Ah. All right, you're probably like, I don't know, same song and dance.
Hey,